Okay, second video on roots of complex numbers, and this is the one with the examples on it. And we've got a roots of unity first up. Z cubed equals 1, where Z is a complex number. We have to solve that. In the previous video we said in general this is the solution, but it's pretty easy when it's roots of unity, and we're on a unit circle too. So let Z equal r cis theta, and we'll get it in polar form. So Z cubed is r cubed cis 3 theta cubed from de Moivre's theorem. Okay, and that r cubed cis 3 theta equals 1 cis theta. Sorry, 1 cis 0 I should say. Because that's what 1 equals. Okay, its modulus is 1, its argument is 0. Now what we do if the angle is a bit more, I mean r cubed is equal to 1, that's straight equivalence, but we need to think more about the angle. So 3 theta equals 0 plus 2k pi. We need to do this step here in order to generate all the possible solutions. Theta then is 0 plus 2k pi all over 3. The 0 we can leave off now, so it will equal 2k pi over 3. As mentioned previously, k is an integer. That allows us to get all the solutions, and we'll know when we have all the solutions, as you'll see soon. Therefore the solutions will be in the form Z equals, we could put a 1 there, we don't need to, cis 2k pi over 3. And we just run through the integer values. So a sensible place to start is when k equals 0. So we have our first root, which we call Z1, is, let's see, we've got sub in 0 for k, it'll be, the whole numerator there would be 0, so that would be cis 0. Now, if you need to, you can write it out in expanded form, so that's cos 0 plus I sine 0 radians, which is 1. So we've got Z2. Now, if it's okay to leave it in polar form, you can leave it like that, or if it needs to be in Cartesian form, we can put it there in that. So depending on what the task requires you to do, and we just keep generating. Okay, we have k equals 2 for the third root, and now for the fourth root we have, and we should get, if we're paying attention in the earlier video, n is 3, so we should get 3 roots. Let's see if we try the fourth. Yes, and that's a repeat, so we don't count that one because that'll be the same as cis 0. So you probably don't need to do that step because we know that it'll be 3 roots because n equals 3. So that's roots of unity question. Essentially we're giving it in both polar form and also Cartesian form of a complex number. You may be asked to draw this in the Cartesian plane, and so this is all on the unit circle. You can see the magnitude is equal to 1 there, okay, and you can see the 3 roots there with their modulus and argument put in, and they're color coded there so you can see the difference. And Z3 is the conjugate of Z2, okay, and geometrically the roots can be represented as points on a unit circle, and they're all equally spaced around, as we said, 2 pi on 3 radians apart. So that's how you represent that graphically, which you may need to do. Now I was going to do 3 examples, but you know what, I've just changed my mind. How spontaneous of me. And I'm just going to show one last example which will hopefully cover you for a significant range of questions you're likely to encounter. So let's do the last example. So we've got to solve this one, and it's in not in polar form, so we need to convert it into polar form. It's currently in Cartesian form. So we've got the modulus of the complex number, which is 32. For the argument, be careful. This one's pretty straightforward because both A and B are positive. It's clearly in the first quadrant there. So it's actually going to be the inverse tan of y on x, or b on a I should say. Not really dealing with vectors, but it's the same process. And that's the, whoops, forgot to put inverse tan. So that's inverse tan of 1 essentially, and that's pi on 4. Don't say 45 degrees please, pi on 4 radians. Let's write it now. So therefore z equals 32 cos I sine pi on 4. So let me say that clearly, z to the power 5 is that, okay, because we were given the equation z to the power 5 is 16 root 2 plus 16 root 2i, so z to the power 5 is 32 cis pi on 4. And just remember from previously how we get z, I've just put that there on the side, and we've got our argument which is pi on 4 plus 2k pi over n, where k is an integer. So usually it's instructive to start at k equals 0. We're going to have 5 roots because n equals 5. And we go through. So 32 to the power 1/5 is 2. 2 to the 5 is 32 in other words. And k is equal to 0, so we have pi on 4 on 5. Now note here, the previous example put it in Cartesian form. Now these aren't exact values. You've got some awkward numbers there, pi on 20, so that usually means polar form is fine. So leave it alone at polar form when you've got things like that. But if that was something like one of the exact value arguments, and it'd be reasonable to ask a student then to convert it to Cartesian form. So k equals 1 is the next, and so we've got that was z1 there, so the root z2, 2 cis, and we keep going. Okay, so that's 2 cis 9 pi and 20 is our second root. I'll just put that one in brackets just so you can see it there. It's a little bit congested there on the side. K equals 2 gives us the third root. So 2 cos I sine 17 pi and 20. Okay, now that one simplifies to 2 cis sine 5 pi and 4. So that's, if you think about it, that's in the third quadrant. That one can simplify into Cartesian form, as you can see. And that one's 2 cis 33 pi and 20. It's best to write it in its principal argument. Remember, that's it there. Now, if we look at that, 20 pi on 20 is pi. Okay, so we need to look at that. So 33 pi and 20 is way around there, so you'd actually use the negative complement there, and so that would more correctly, preferably be written as that. You could be asked, that would be a difficult one, but you could be asked to do the Cartesian figure for that one. Just a quick sketch to keep the video short. So the magnitude of this, these roots, we call that A. If you go back to the first video, they're 2, and there's 5 of them spaced evenly around, and they're 2 pi on 5 radians apart, equally spaced, which is a little bit tricky to draw on this one. And you just keep going around. That's a very poor attempt from me, but you just basically make them all the same. They should be equally done, and this one will be a bit tricky because it's got some awkward angles. Perhaps you wouldn't be asked to do the Cartesian drawing or the Argand drawing for it, but you can see that they are all the same magnitude or same modulus, and they're a gap of 8 pi and 20 apart, which is 8 pi and 20, or 2 pi and 5 apart radians. Okay, and you'd have 5. So that's not a very good diagram, but you get the idea hopefully.